This is the second part of my introduction to Laplace transforms. In the first video, we gave the definition of the Laplace transform, talked a little bit about general integral transforms, and then did two examples of calculating Laplace transforms. In this video, I want to do two more examples of calculating Laplace transforms, and then show that the Laplace transform is a linear operator. So here we go. I want to do the Laplace transform of e to the at. All of a sudden, I'm thinking I should have had more breakfast. Okay, by definition, the Laplace transform of this function is the integral from 0 to infinity of e to the minus st times the function that I have, e to the at. A is just a constant, right? dt. So I can combine these into a single exponential where you're just adding the exponents. And then I'm going to also factor the t out. So this would be a minus s times t, right? Minus st plus at, factor the t out, dt. So this can now be integrated with a u substitution with u equal that a minus s times t. And so I get 1 over a minus s e to the a minus s times t, evaluated with t between 0 and infinity. So plugging them in here, I've got 1 over a minus s e to the a minus s times infinity minus the minus 1 over a minus s, plug a 0 in here, e to the a minus s times 0. Now, this is always the kicker, what's happening with that infinity? If this is going to not diverge, it's because this infinity is doing something. And this exponential, e to the, well, exponential functions, of course, either do this or they do that, depending on whether this number here is positive or negative. We want it to do this because as t is going, t is going to infinity, we want this to be headed towards 0. So I need a minus s to be a negative number. A minus s has to be less than 0. That tells me that a has got to be less than s, so s has got to be bigger than a. This is a minus s. So as long as s is greater than a, then this part right here is a 0. I'm going to distribute the minus sign in here to write that as plus 1 over s minus a, and then I have e to the 0, which is 1. So the Laplace transform of e to the at is 1 over s minus a, and s has to be greater than a. Okay. Laplace transform of an exponential. Let's do, how about a piecewise function? My next example here is this, where I have, actually it's a pretty simple piecewise function. It's 0 up until you get to a, and then it comes up to 1. Let's look at the Laplace transform of this. I'm doing this one just as a really basic example of how how you're going to handle a piecewise function. And I think in my limited knowledge of how these are used, piecewise functions is one of the strengths that the Laplace transform has. It has a way of dealing very nicely with piecewise functions, where our general practices on solving differential equations doesn't really handle discontinuities very well. Anyway, Laplace transform is the integral from 0 to infinity e to the minus st times this function, right? Times f of t dt. Well, this function is piecewise, so I'm going to have to break this into pieces. From 0 to a, this is e to the minus st times 0. And then from a to infinity, it's e to the minus st times 1. Right? A piecewise function, I can break the integral up into the two pieces. Well, e times 0 is 0. So that's beautiful. That's just a 0 right there. So I'm just left with the integral from a to infinity of e to the minus st. which I can integrate as minus 1 over s e to the minus st, evaluate it between t equals a and t equals infinity, minus 1 over s e to the minus s times infinity, minus 1 over s e to the minus s times a. Again, the infinity, this is where something might go wrong. In order to keep it from going wrong, this needs to be going to 0. This has got to be e to the negative infinity. So s is going to have to be positive. If it is, that's a 0. And I get e to the minus s times a over s as long as s is positive. Okay. Piecewise function, piecewise integral. Right, you break it up into the pieces. It would have been pretty cool. We could do another example, but I'm not going to. Where if you stuck a 1 here and a 0 here, so this was a 1 and that was a 0, I wouldn't even have had to deal with the infinity because I'd have been integrating 0 from a to infinity. And you'd have just gotten stuff out of whatever this was. Right? But in this case, the 0 was in the first part and the 1 was in the second part. So, now, last thing I want to do in section 6.1 here is to take a look at the linearity of the Laplace transform. Okay. The Laplace transform is an operator, right? You put a function in, you get a function out. And it turns out that it's a linear operator. Right? So if I have two functions, f1 and f2, and I multiply them both by constants, and I add them up, that's called a linear combination of the two functions f1 and f2. And I want to take the Laplace transform of that and see how it's related to the Laplace transform of f1 and the Laplace transform of f2 individually. So here we go. By definition, the Laplace transform is the integral from 0 to infinity of e to the minus st times this function, c1 f1 plus c2 f2 dt. But now there's a lot of linear things going on here because you have a distributive property, which means you can distribute to both of those. You have the commutativity of multiplication, so when I multiply this times c1 f1, I can write those in any order I want. So I got the integral from 0 to infinity. I'm going to write it as c1 e to the minus st times f1 plus, and again, this times that, c2 e to the minus st times f2 dt. But now, the integral, we established this way back in Calc 2, the integral is a linear operator. So this can be written as, the integral of a sum is the sum of the integrals. So I got the integral of c1 e to the minus st times f1 dt plus the integral of c2 e to the minus st times f2 dt. But integrals also commute with multiplication by a scalar, so multiplying before or after the integral, it doesn't make any difference. So this is c1 times the integral from e to the minus integral from 0 to infinity of e to the minus st times f1 dt plus c2 times the integral from 0 to infinity of e to the minus st f2 dt. But this right here is the definition of the Laplace transform of f1. So this is c1 Laplace transform of f1 plus c2, and this bit right here is the Laplace transform of f2. So the Laplace transform of c1 f1 plus c2 f2 is c1 times the Laplace transform of f1 plus c2 times the Laplace transform of f2. To me, this says two things. Picture, for instance, if c1 and c2 are both 1. This would say the Laplace transform of f1 plus f2 is the Laplace transform of f1 plus the Laplace transform of f2. Likewise, if c2 is equal to 0, so just cover that up and cover this up, then the Laplace transform of c1 f1 is c1 times the Laplace transform of f1. So generally when I think of linearity, there's two properties you need. Essentially distributing over addition and commuting with scalar multiplication. This gets both of them. If you can do that, you can do both. So anyway, there you go. The Laplace transform is a linear operator.